So welcome back to the new lecture on time-dependent perturbation theory. Today we are going to discuss about the transition probability for a harmonic perturbation using time-dependent perturbation. Okay, so suppose if your Hamiltonian is of the form H0 plus V, where H0 is the completely solvable Hamiltonian and V is can be treated as a perturbation part, where V will be non-zero for some amount of time, maybe for the duration of tau. Okay, and it is zero otherwise. Okay, so if that is the case, then obviously the system will be in the energy eigenstate of H0. Okay, or it would be the superposition of energy eigenstates of H0. Now whenever the perturbation is switched on, then the system can move from one state to the other state. Okay, so there can be a transition. Okay, so due to perturbation, so perturbation is V of t, system can change from state, some state, initial state psi I to the final state psi f. Okay, so we already found the expression for the probability of this transition. So the probability of transition from the state I to state f in the first order approximation, which is given by a modulus of minus I by h cross integral 0 to t, the inner product psi f v psi I e raised to I omega fi t prime dt prime. Okay, so here v can be a function of t prime. Okay, so mod square. So this is the transition probability in the first order approximation. Okay, so if you have a second order approximation, then there will be one more term and so on. Okay, so we are discussing, we are limiting our discussion only in the first order approximation, so we are not going further. So we already discussed the transition probability if the perturbation is constant in time for this time interval. Okay, now today we are going to discuss about the same problem about the harmonic perturbation. Suppose your perturbation is a function of t if it is harmonically varying with time. So harmonically varying with time means it can be written as some constant into e raised to I omega t plus that should be, it should be um, so I've added both e raised to I omega t and e raised to minus I omega t because this perturbation must be Hermitian operator. Okay, because only Hermitian operator can be observed in quantum mechanics. That is why I've put both the terms. Okay, so this small v and small v dagger is just a constant. Okay, so this v of t takes this form for the time intervals from 0 to tau, and it is 0 otherwise. Okay, so if this is the case, then what would be the transition probability? So we can easily found it. I just substitute the expression for this capital V of t here. Okay, so we can do that. So the probability transition P I to F up to the time t equal to modulus of minus I by h cross integral 0 to t e raised to I omega fi t prime inner product the psi f small v e raised to I omega t plus small v dagger e raised to I omega t psi I. Okay, it should be t prime and dt prime mod square. Okay, so it is possible that I can split this into two terms. So minus I by h cross mod square simply become 1 by mod h cross square integral 0 to t e raised to I omega fi plus omega times t prime inner bracket psi f v psi I dt prime plus integral 0 to t e raised to I omega fi minus omega times t prime. Okay, then inner bracket psi f v dagger psi I dt prime. Okay, whole square. It's good. Now this psi f v psi I would be independent on time, so that can be taken outside of the integration. So this become 1 by h cross square modulus of psi f v psi I square. Then I can take this integration. So this integration will take e raised to I omega fi plus omega t prime divided by I times omega fi plus omega, and the limit from 0 to t and its mod square plus 1 by h cross square can write psi f v dagger psi I mod square, then modulus of integrate the remaining thing e raised to I omega fi minus omega t prime divided by I times omega fi minus omega mod square, plus there will be a cross term here. Okay, because if you this two term addition mod square would give, so a plus b the mod square should give the mod a square plus mod a square times plus 2 times mod a into mod b. Okay, now that cross term can be neglected because that would be very small compared to these two terms. So the cross terms I am neglecting here, so I'm using an approximation there. So cross term is neglected, so this will be the final two terms. Okay, so I can give the limit and we'll get the result. Okay, so if you do it carefully, so this would become 4 by h cross square modulus of psi f v psi I square sine square omega fi plus omega times t by 2 divided by omega fi plus omega square plus again 4 by h cross square the inner product psi f v dagger psi I square. Only difference is sine square, it become omega fi minus omega times t by 2 divided by omega fi minus omega square. Okay, it is not a surprise to get this result, because what we'll do is, if you look at here, if you put the limit, so you'll get two term. One is e raised to omega fi plus omega t minus 1. So from that you can take e raised to I omega fi plus omega t by 2 commonly outside. Then we'll get a sine term here, some 2i sine term here. So I will cancel and 2 square become 4, and e raised to term would cancel when you are taking the mod square. So I think the same steps we have taken when we are discussing about the constant perturbation. So we can repeat those steps. Okay, so you can just refer derivation of the transition probability for constant perturbation. Okay, so it is the same similar result. So I will just show it here. I have the result here. Okay, so this is a thing that we have done. So if you integrate it, you'll get e raised to some omega phi t minus 1 by I omega phi the mod square. So only difference is, instead of e raised to I omega fi, we have omega fi plus omega, and omega fi plus omega. Okay, you have to just replace omega fi to omega phi plus omega. That is the only difference. Okay, so if that is the case, then what I have to do is, here we will be doing it. We will be taking commonly taking e raised to I omega fi t by 2 outside, and we'll get this entire term. This entire term will take the form of 2i sine omega phi t by 2. Okay, so that is what we have done here. Okay, and so you will get some 2i sine omega phi by I omega phi. So I will cancel, and mod square of this would be 1. So finally it will be 4 by h cross square in this term. Okay, so only I have to do, I have to replace this omega fi to omega phi plus omega in one integration, and in another integration I have to replace this omega phi to omega fi minus omega. So that is the only difference when you are going from the constant perturbation transition probability to harmonic perturbation transition probability. Okay, so we can use the final result also. So in the finally the result is this. Okay, so the same result we can use it there. So what would be the final result? So this can be written as, so finally when t tends to infinity, what would be our result? So when t tends to infinity, this integration, the result of this integration will take the Dirac delta function. So therefore I can write it's equal to 2 pi t by h cross mod psi f v psi I square, and Dirac delta omega phi plus omega plus 2 pi t by h cross inner product psi f v dagger psi I mod square Dirac delta function omega fi minus omega. Now what was omega fi? So omega fi is basically, it's called the transition frequency. It is ef minus ei h cross. Okay, so there should be an h cross here. Sorry to write. There should be h cross in both term. So therefore I can write in terms of energy as 2 pi t by h cross mod psi f v psi I square, the Dirac delta function ef minus ei plus h cross omega plus 2 pi t by h cross, the inner product psi f v dagger psi I mod square, the inner product ef minus EI, sorry, minus H cross omega. Okay, so Dirac delta function would be non-zero if the argument is 0. Okay, so therefore this would happen, this will be non-zero when EF equal to EI minus H cross omega, and this would be non-zero, this term would be non-zero when EF equal to EI plus H cross omega. So that is when the final state, the energy of the final state, if it is less than H cross omega time H cross omega less than the initial state, then this term would be non-zero. So therefore this term corresponding to this entire term corresponding to the transition to the lower state. Okay, so this corresponding to de-excitation or emission. This is basically emission process. So the energy would be emitted outside. And what about here? Here final energy must be H cross omega H cross omega greater than the initial energy state or initial energy. So therefore this term corresponding to excitation. Okay, so excitation, or I can also write absorption. So the energy would be absorbed from outside. So if you have a harmonic perturbation, so there are two possibility. So either there can be emission of energy, the state can be lowered, the energy of the state, energy of the system can be lowered to a lower state. Okay, and there can be excitation possibility also. The system can be excited to higher energy by absorbing energy from outside. So this H cross omega, we can refer it as a photon energy if you want. Okay, so either we can get absorption or emission. So energy gets absorbed or energy gets emitted. Okay, so the excitation will by dependent by the second term. So that is the term containing V dagger, and this de-excitation is controlled by the term containing V. Okay, so now I have taken this V and V dagger, so it can be of different symbol also, A or B. Okay, in general. So this mod square, so the psi of V psi I mod square will actually proportional to the de-excitation probability, and the mod psi of V dagger psi I mod square will give the excitation probability. Okay, so we can conclude this session. So if we have a perturbation, if we have a harmonic perturbation in the form V e raised to I omega t plus V dagger e raised to minus I omega t, then there can be two process, either absorption or emission. Okay, so which corresponding to absorption? The absorption, the absorption is controlled by V dagger term, and the emission is controlled by V term. The absorption is controlled by V dagger, and the emission is controlled by V. Okay, so here we have just discussed about the transition probability, and finally we can have the expression for transition rate. So transition rate usually will be denoted by symbol gamma IF. Okay, so there are two possibility, the gamma IF corresponding to absorption. So how will I write that? So that would be equal to 2 pi by H cross the modulus of psi f. The absorption is controlled by V dagger psi I square. The Dirac delta function EF minus EI minus H cross omega. So this will be non-zero only if EF equal to EI plus H cross omega, and the transition rate corresponding to the emission, that is 2 pi by H cross mod psi f v psi I square, Dirac delta function EF minus EI plus H cross omega. Okay, so that's about the discussion. So this absorption, I can call it as the absorption of the system by absorbing energy from outside, maybe a photon, and this emission we can refer to it as stimulated emission, because we have a perturbation, and due to the perturbation, the system emits energy. So this kind of emission is called stimulated, and this is simply absorption. Okay, so this is not corresponding to spontaneous emission, because we need to have a perturbation from outside. The external perturbation is required for this kind of emission. So this is actually the stimulated emission. So you can summarize it using the figure. So suppose if you have two states, so the term V dagger refers to absorption, that is, the system move from the initial energy EI to the final energy EF by absorbing H cross omega energy, and this H cross omega energy I can refer it as a photon. Okay, now the term V gives the transition from initial energy to the final energy. Okay, so there is a reduction in energy, so this EF is equal to EI minus H cross omega. Here EF is equal to EI plus H cross omega, and here the energies get emitted, H cross omega is get emitted, and this emission is called stimulated emission, because this emission is due to this perturbation term. Okay, without this perturbation term, if V is 0, what would be transition probability? The gamma IF emission would be 0. Okay, there will not be any emission at all. Okay, so therefore this kind of emission I cannot call it as a spontaneous emission. So this kind of emission I have to call it as stimulated emission. But for absorption we will not use the term spontaneous or stimulated. It is always stimulated, because some perturbation is required for the absorption process. Okay, for only for the emission we have a choice. There can be a stimulated emission or spontaneous emission. Okay, so we can stop it here. So before stopping, we can just summarize what we have discussed today. Okay, so our aim of today is to find the transition probability for a harmonic perturbation. So if you have this V, the perturbation term in the form of V plus e raised to I omega t plus V dagger e raised to minus I omega t, where this small v is a constant in time. Okay, then it is very easy to calculate the transition probability in the first order, because in first order approximation is expression for the transition probability, and we have just substituted the expression for v there, and we found that we get two terms, and actually the third three terms will be there, but the third term we are neglecting because the third term would be very small, and its contribution would be very small compared to the first two terms. So that is why we have neglected the third term. Okay, since we have neglected the third term, we have only two terms present. Now these two terms corresponding to some sine square function. Okay, so these terms corresponding to sine square function. So this sine square function, if you plot it, uh, using a graph, how it will be look like? Okay, so this sine square omega fi plus omega t by 2 divided by omega fi plus omega square. And if you plot this graph, you will get the plot would be like this. And here this is omega fi plus omega. So when omega fi plus omega is 0, we'll get maxima, and this peak would increase. This peak would be proportional to t square by 4. So this peak would increase when t increases, and the width would decrease when t increases. Okay, so when this omega, so this corresponding to uh, pi by 2 pi by t, I think is corresponding to pi by t. So this width of the peak decreases when t increases. So when t is very large, when t is very large, this function will take the form the Dirac delta function. Okay, so that so these things we have already discussed while we are discussing the constant perturbation theory. Okay, not constant perturbation theory. That is the time dependent perturbation with the constant perturbation term, and we have found the transition probability is a Dirac delta function. So same expression we comes here, but there is some difference compared to the constant perturbation. We have two terms. The one term corresponding to the absorption term, and the other term corresponding to the emission term. There is no such absorption or emission in case of constant perturbation. So in case of constant perturbation, the final energy level must be same as the initial energy level. This EF must be equal to EI. But whereas in the case of harmonic perturbation, the final energy level and initial energy level can be separated by an amount of h cross omega. Okay, so there are two possibility. So either we have absorption or emission. Okay, so this absorption is controlled by V dagger term and emission is controlled by V term, and we can define the transition rate. So transition rate is a transition probability per unit time. So if you divide it with time, then the transition rate will take the form 2 pi by h cross. For absorption, it takes this form. So this term corresponding to absorption, and emission term can be written here. This emission is not spontaneous emission. This emission is basically called stimulant emission, because we need an external perturbation for to in order to have such kind of emission. Okay, so we don't have the answer for the question that how the spontaneous emission occurs. Okay, so that we have to discuss in detail. So we'll discuss our we'll stop our discussion here. So in next we will discuss about the interaction between the atom and field. So actually that discussion will give the reason behind the spontaneous emission. So first we'll discuss the classical treatment, then we'll go for the quantum treatment. So there we'll get the idea about how the spontaneous emission occurs inside the atom. And the spontaneous emission is basically the main reason for the natural light. Okay, so all the natural light sources is basically from the spontaneous emission. So not only that, even our the usual light sources are also producing light through the spontaneous emissions. Okay, so so thank you everyone for watching this. So in next class we'll discuss about the atom field interaction. Okay, so by the time, bye.